In this lecture, we will look at the issue of DC biasing of a transistor circuit in a bit more detail. We did discuss how to use the approximate DC model of a bipolar junction transistor to analyze DC biasing circuits, but I am pretty sure most of you must have realized that we could have perhaps done equally well if we had ditched the approximate model and instead just brought in the approximate equations instead. So, the approximate model for a transistor in the active mode essentially gives you these two equations, that VBE, the base emitter voltage, is V gamma, the cut-in voltage, and IC is simply beta IB. Now, of these, the very first one, VBE equal to V gamma, is actually valid for an NPN transistor, because for an NPN transistor, base emitter voltage is positive in the active mode, whereas for a PNP transistor, VBE should be minus V gamma. The IC and IB are both into the transistor for NPN or both out of the transistor and hence negative for PNP. So, IC equals beta IB stays equally valid no matter whether you are talking of NPN or PNP. However, there is one important term missing in this approximation, and that is the current that would flow, the collector current that would flow even if IB were 0. This is ICO, CEO, or the collector to emitter current in the absence of the, or emitter to collector current to be more precise, with the base open. Now, ICEO, as we have seen in an earlier lecture, is related to the reverse saturation current of the collector base reverse bias, ICO, by ICO times beta plus 1. So, ICO is the collector current that would flow if the emitter were open, and ICEO is beta plus 1 times that. Now, you might think that even though ICEO is much larger than ICO, it's still typically much smaller than IC. IC typically is of the milliampere range, whereas ICEO is in the microampere range. However, the reason why I am still including this term in our more careful DC bias analysis is simply this. ICO is strongly temperature dependent. As I had explained earlier, it roughly doubles for every 10 degrees Celsius rise in temperature. Now, this may seem like a very tiny thing given the fact that both ICO and ICEO are rather small. However, what this really shows is that if you have a circuit in which IB is held fixed by external constraints, then the change in IC as temperature changes is essentially beta plus 1 times bigger than the change in ICO. And this might actually become quite a bit of a problem in circuits where IB is held fixed by external circuitry. As we will soon see, the most basic common emitter amplifier is actually of this kind. Now, the trouble there is that as temperature rises, ICO changes, ICEO changes beta plus 1 times as much, leading to a change in IC, which may very well shift your bias point to a value which is unacceptable. Even more disastrously, this increased current in the collector would give rise to higher heating that might produce a further temperature rise, which would perhaps lead to an even bigger rise in ICO, causing again a further temperature rise, and so on, and the whole thing might snowball, and you may have what is called thermal runaway, and your transistor may get destroyed. So, circuits where IC changes rather rapidly compared to ICO as temperature rises, even if the change is very small, for them temperature rise may become quite a big problem. So let us now try to use these equations, namely VBE equals V gamma and IC is beta IB plus ICEO, to analyze a simple circuit which is called a fixed bias circuit. Now, as you can see, in the fixed bias circuit we are actually using only a single voltage source which has been marked VCC. Actually, this is the case where the voltage source is doing double duty as a collector bias battery as well as a base bias battery. The reason why we can do that is that in the common emitter configuration, the ground point or the reference point is the emitter, of course, and in order that the transistor be in reactive mode, the base has to be positive with respect to the emitter. This, of course, is for the NPN transistor, and the collector has to be positive with respect to the base, which means it also has to be positive with respect to the emitter. So here, compared to the common reference point, both the base and the collector are positive. So you can actually achieve that using a single battery. Contrast this with the common base amplifier. There, of course, if you wanted the active mode, then the emitter would have to be negative with respect to the base, whereas the collector would have to be positive with respect to the base. And this would mean that you can never achieve that with one single battery. Now you might ask, what's so special about using one single battery? And the answer is simple. It's economics. The battery happens to be the single most expensive piece of equipment in this circuit. You have two resistors and a transistor and some wires, each of which really costs next to nothing compared to a battery. So using two batteries would effectively double the cost of the circuit. So if you can get away with using one, then it's great. So that's exactly why we do this. We just use a single battery to drive the circuit. So we are connecting the single battery via RB, the base resistance, to the base, and via RC, the collector resistance, to the collector. And the emitter, of course, is grounded. Once again, let me remind you, this is not the full amplifier. This is just the DC biasing part of the amplifier. The full amplifier, of course, will also have a signal which has to be connected to this, and also you will have to take the output somewhere. There is the AC output somewhere. We are ignoring that for the time being. In this lecture, I am going to solely focus on the DC biasing. So now, let's just try to write down the bias equations, which will simply follow from Kirchhoff's laws. So if I use Kirchhoff's voltage law along the loop which this red line indicates, this will get an equation. But first, let me clarify what I mean when I say the loop which the red line indicates. Notice that this point is marked VCC. What that means is that there is a battery of magnitude VCC connected between this point and the ground. So basically, although we did not say that, if you followed across the battery, you would really start at the ground, and now this red line makes you come back to the ground. That's why this really is a loop. It starts at the ground, comes back at the ground. So if we now apply Kirchhoff's voltage law for this loop and just find the net voltage rise across the loop, you are supposed to get 0. So what will you get? You get VCC, which is a rise, then a drop of IBRB, so VCC minus IBRB, minus this drop across the base emitter junction, VBE. So VCC minus IBRB minus VBE must be 0. So this is our equation. Of course, we will use the approximation that VBE is V gamma. So we will end up with IB equals VCC minus V gamma by RB. Notice that in this circuit, the value of the base current is sort of fixed by the passive parameters VCC and RB. These are parameters which are controlled from outside. They don't depend on the transistor. And they are much easier to control and keep fixed. Now, of course, the parameter V gamma in this equation, the base emitter voltage of the transistor, really depends on the transistor, and it of course depends on the operating situation of the transistor. However, VBE is almost fixed at this V gamma value, which is around 0.7 volts or something, depending on the kind of material your transistor has. Now, let me clarify a point here. We keep on using VBE in various calculations where we just replace it by V gamma and tend to forget about it after that. This might make people think that VBE is a rather unimportant parameter. After all, it's always V gamma, so what's so great about that? The fact of the matter is, as far as transistor operation is concerned, it is VBE which actually does all the controlling. The base emitter forward bias dictates how many electrons will flow from the N-type emitter to the base, and then of course will get swept on along to the collector. Changing VBE will of course drastically change the currents. However, it is this very fact that VBE affects currents so strongly that is the reason behind our treating VBE more or less as a sort of unimportant parameter in calculations, because VBE changes very slightly, and that change is enough to cause all the changes that happens in the other currents or voltages. So, as far as calculations are concerned, we just approximate VBE by this fixed value of V gamma and forget about it. In a sense, it's paradoxical. The very fact that VBE is very good at controlling currents is the reason why people hardly give it the credit for being the important parameter it really is. But be that as it may, in a circuit, as I said, VBE hardly changes, so IB is more or less fixed by the external parameters. This has nothing to do with the transistor. And as I warned, this is precisely the situation where change in temperature is going to give rise to quite a comparatively large change in the collector current, and that might get out of hand. So of course this will give rise to the collector current, which is IC equals beta times IB, beta times VCC minus V gamma by RB, plus beta plus 1 times ICO. So this gives us the current IC. The only other thing that is remaining to calculate is VCE, and that's easily done by taking a look at the other loop which is there in the circuit, which is just this line. Of course, why is this a loop? Because it starts at the ground, goes to VCC and then comes down straight. So this gives you VCC minus ICRC minus VCE, whatever the drop is from the collector to the emitter, and that has to be 0. So VCE, the collector emitter voltage drop, has to be VCC minus ICRC. So this completes our calculation for the bias in the fixed bias circuit. And if you just use numerical values, I'm pretty sure almost always you will find that beta plus 1 ICO is too small compared to this. And we might just as well have used IC equals beta IB if I wanted numerical values for the collector current and hence for the collector emitter voltage. Once again, let me stress that the reason why I have included the ICO in our calculation is to keep track of the fact that temperature variations might cause a big change in IC. Now, there's one caveat here. You have to be careful about one thing. All this calculation has been done assuming these two equations, which of course comes from the active mode approximation of the transistor. So these calculations will be valid only if the transistor is in the active mode. So after we do the calculation, we should really check whether the transistor is in active mode. And this is very important. If you want to ensure the transistor is in the active mode, what you must ensure is the drop across the resistance RB must exceed the drop across the resistance RC. Why? Because that is what will make the base go below the collector in voltage, which is what you need for the reverse bias. Remember, the other ends of RB and RC are both connected to the same voltage VCC here, which is the price we pay for using one source instead of two sources. And as a result, this drop across RC must be less than the drop across RB if you want to have active mode. This also means that the sizes of the resistances cannot be arbitrary. So as IB is typically much smaller than IC, you will have to choose a much larger value for RB. Okay. Now, having said that, let us now discuss the issue of bias stability. What happens to these bias values? The bias values of course include all four things: IB, VBE, IC and VC. Now I have actually written down the bias point or quiescent point values for the fixed bias circuit, and as you can notice, I have just written down the IC value and the VCE value. I have not written down the VBE because, as I explained, VBE is nearly fixed at V gamma, so we don't really bother about that at this stage. And IB, something we figured out there, and in fact is just this thing in the bracket here, is again a quantity which does not change unless you drastically change the circuit parameters, the other parameters in the circuit. Okay. Now, the question that I am discussing here is that of bias stability, which will tell us why the fixed bias circuit that we described here, although is very simple and just uses 2 resistors and a single battery, so it's cheap, is still not a very good choice. So let us start by looking at the equations for IC and VCE again. Of course, you can see that VCE depends on IC, so let us just focus on this expression for IC. Now, in this expression for IC, you have beta, and beta is a rather fickle parameter. Beta depends on the transistor, but when I say it's a fickle parameter, that's because beta actually changes somewhat, well, quite a bit actually, with temperature and the operating voltage. So if your voltage changes, if the temperature changes, beta changes quite substantially. What's actually even more important perhaps is that even within the same family of transistors, it changes quite a bit from transistor to transistor. Now beta, remember, is alpha by 1 minus alpha, where alpha is the ratio of the fraction of the electrons which enter into the base from the emitter, which are swept onto the collector. So that's the fraction that you're looking at. Now this fraction is controlled strongly by the way the transistor is designed, and depending on how precisely you design the transistor, alpha is more or less fixed. But even this more or less fixed means that it's not perfectly fixed. Within even an identical family of transistors constructed identically, as identical as possible, alpha would vary a bit. But if you think about it a bit, since alpha is very close to 1, any variation in alpha, a small variation of alpha, can lead to quite a large variation in alpha by 1 minus alpha, which is the value of beta. So beta actually changes quite a lot when you go from one transistor to another within the same family. So suppose you have designed a circuit, taking the values of beta, etc. from the manufacturer's data sheet, and then you actually connect your transistor. It might very well happen that the beta is quite different from the value that is given in the manufacturer's data sheet, which would mean that the IC value you get from your circuit may substantially change from the IC value that you calculated or that you wanted your circuit to have. When you're designing a circuit, that can be quite a problem. Okay, and even if your circuit is working fine with the particular transistor that you have chosen, it might so happen that your transistor burns out or somehow ages and just goes bad, and you replace it by another transistor of the same family. It might so happen the beta for that transistor is so different from the one that you have that IC will again change quite a lot. This is why this is not a great design. It depends strongly on the value of beta, the IC value, and hence the VCE value. And if the bias point moves a lot, you may move from the active region to somewhere where you are very close to either cutoff or saturation, or you may move to regions where the characteristic curves are not equally spaced out. I have not explained earlier exactly what this equally spaced out thing means, or why is that significant. The answer simply is that after all, the biasing is not the be all and end all. You are making an amplifier, which means you will give a signal, and when you give a signal, your input voltage and current will vary. Now, if the characteristics are evenly spaced, then they will ensure that the output currents and voltages will vary in proportion. If they are not uniformly spaced, it might very well happen that the output will have a variation, but it will not faithfully mimic the input, and you will end up with a lot of distortion. Be the case whatever it may, strong variations in the bias point is not a great idea, and so that's one reason why the fixed bias circuit is not so good, because the bias point, IC and VCE, changes drastically with changing beta. So you may end up with an unacceptable bias point because beta has drifted. Whatever be the reason, maybe temperature has changed, maybe you have to replace the transistor. Changing beta may make your circuit go from a usable, nice circuit to one which you simply can't use. Even more than this variation of the circuit bias point with beta, the larger problem would be the fact that the bias points here depend strongly on ICO. Why is that the issue? Remember, ICO being a minority carrier current depends drastically on temperature. So take a note of what happens with temperature. As temperature changes, this factor here does change somewhat. As I said, beta does depend on temperature. So does V gamma in a way. But these two factors really pale in comparison when you come to this one. Here, ICO is a very rapidly changing function of temperature, though it's rather small. And because of the beta plus 1 factor sitting in front, IC is rather sensitive to temperature change. So for the fixed bias circuit, already we have seen that this dependence of IC on beta is a problem, but a bigger problem is the fact that IC changes rather drastically with temperature because of this factor beta plus 1 sitting in front of the ICO. Of course, if IC changes drastically with temperature, so will VCE. And as a result, you might have thermal runaway, as I explained. Temperature rise may cause the collector to heat more, that would cause further temperature rise, and so on. But even if something so drastic does not happen, it might very well happen that the bias point moves quite a long way from where you intended it to be, and as temperature changes, it might drive the bias point close to saturation or into saturation, and then your circuit will cease to work as an amplifier. So that is quite a bit of a problem. So the important thing is, for fixed values of circuit element, IC depends on the transistor parameters V gamma and beta, as well as ICO, and ICO depends strongly on temperature. Now, circuits have to be specifically designed to compensate for this dependence. As we discuss right now, the fixed bias circuit, though simple, is not a great circuit, simply because it depends strongly on changes on beta and changes of temperature. Now, how good is your circuit? How good is your circuit design? That, in order to keep track of that, we can think of a measure which is called the stability factor. In this case, this essentially measures how well does your circuit stand up against variations of temperature. What you do is simply calculate this partial derivative. The partial derivative of IC with respect to ICO, which of course is the other quantity which I did not write here, which IC depends upon. So del IC delta ICO at fixed values of V gamma and beta. And of course, very often, especially when you are experimentally determining this, you don't really determine the partial derivative, you calculate the change in IC over the change in ICO, maintaining V gamma and beta at fixed values. So this is called the stability factor. Frankly speaking, this should have been called the instability factor, because a larger value for S really means the circuit has a higher chance of being thermally unstable. The bigger S is, the more strongly IC responds to changes in ICO and hence to changes in temperature. So the whole game of trying to design a better circuit as far as bias stability is concerned is one in which you try to make S small. Now, there are two other instability factors, again pretty easy to understand. They are the partial derivatives of IC with respect to beta and V gamma. Of course, the other two transistor parameters, ICO, two of the three transistor parameters among beta, ICO and V gamma being constant for the particular derivative that you are looking at. So these are called the they are not called the instability factors, they are called stability factors, S prime and S double prime. But as for S, larger values for these stability factors are also indicative of an unstable circuit. Now, of the three, S is the one which is the most often talked about, because that's the one which actually points at the biggest danger. S prime is also quite important, but as we will soon see, in most circuits, controlling S and controlling S prime sort of happens together. So, one important formula which will be quite useful for calculating S starts from this. The derivation of the formula starts here. You start with IC equals beta plus 1 ICO plus beta IB, which of course is nothing but our approximate equation for the transistor collector current in the active mode. All I have done is I have written the ICO term first, just to indicate that there is a term which is getting precedence in our thought process right now, let us just differentiate this partially with respect to IC, holding VC, VBE and that is V gamma and beta constant at this stage. So if you do that, of course you get 1 on the left hand side. On the right hand side what you get is beta plus 1 divided by S, del ICO del IC at constant V gamma and beta is nothing but 1 by S plus beta times the rate at which IB changes with IC. This formula will tell you that DIB DIC and B and S are related to each other. Simply by this formula, you can just manipulate it simply by moving the beta DIB DIC to this side and then dividing by it. So just answer with this quantity. So this is the useful formula that I am talking about. For a given circuit, if you can find out the rate at which IB changes with IC, all transistor parameters staying the same, then you have the expression for the stability factor. Now just to put it to the test, in the fixed bias circuit, IB is controlled by the bias voltage VCC, bias battery, by the value of RB and the value of V gamma, which we, for all practical purposes, we take to be a constant. Which means that IB is actually independent of IC, because if you change the transistor, change the temperature, IB will not change. So DIB DIC for our purpose, for the fixed bias circuit, is 0. And hence, what you end up with is S of just beta plus 1. This of course is something we could have easily figured out from the direct equation that we wrote down. But it's good to see that this is confirmed. It's just telling us that when you change temperature, ICO changes. When IC changes, beta plus 1 times as much as ICO changes. So this is a rather large value for the stability factor, indicating that the common emitter fixed bias circuit is strongly thermally unstable. So good circuit designs would try to reduce the value of S as much as possible. So let's now talk of one such good circuit design, or at least an attempt at a good circuit design. This is a circuit which is called the collector to base bias. Notice what we have done is, instead of connecting the base battery RB between the base and the collector bias battery of VCC, what we did here is connect the RB resistance between the base and the collector. So you are basically biasing the base via the collector. Now in this case, what is important is to realize that the current flowing through RB, of course, is directly flowing into the base, so that is IB, but the current flowing through RC is really not IC, despite the name RC. IC is the current flowing into the collector, and so the net current flowing out of this node here is IB on this side and IC down. So the current flowing into the node, which is the current flowing through RC, must be IC plus IB. So if we now use this information and write down Kirchhoff's voltage law for this path, what we will get is VCC minus IC plus IB into RC minus IB RB minus VB equals 0. And if I just want to differentiate this with respect to IC, keeping the circuit parameters VCC, RC, RB the same, and also considering VB to be independent of these things. Anyway, remember, to calculate S, we have to take a partial derivative with VB constant anyway. So let's do that. If you just differentiate this with respect to IC, what you are going to get is DIB DIC times RB plus RC equals 0. That gives us this value for DIB DIC. And if we put this back into our master formula for S, we end up with S equals beta plus 1 divided by 1 minus beta DIB DIC. That was the formula, and that gives us this factor here. So notice that the denominator here is larger than 1, which means S is smaller than the fixed bias value of beta plus 1. So we have managed to improve the value of S. We have made the circuit more thermally stable. Of course, how much more thermally stable have we made it? That depends on how on the relative value of RC and RB. If RB were very much bigger than RC, of course, this ratio here would have been nearly 0 and this would have been almost beta plus 1. So not much of a change. But remember, in the fixed bias circuit, we really needed RB to be much bigger than RC in order that the drop across RB be bigger than the drop across RC, which was in turn needed to ensure that the transistor is really in the active region, that is the collector base junction is reverse biased. Here on the other hand, the collector base junction will be reverse biased anyway, because notice that there is this resistance connected between the collector and the base. So any current flowing through that will make the base go lower than the collector. So at least in this circuit, we have no worries about saturation. So as a result, we can move away from using a large value of RB, which would mean that I can make substantial improvement on the value of S. So this looks like a pretty good circuit. No worry about saturation and a much smaller value of S. But let's wait a bit. Let's just take a look at some other aspects of this. This definitely is an improvement over the fixed bias circuit. But if you look at the equation once again and just try to find out a formula for IC, now we're going to take a look at the beta dependence. And as far as the beta dependence is concerned, we can just ignore the ICO term. That's really very small. Let's just use the fact that IC is almost beta IB, and that's much bigger than IB. So in this expression, you can just replace IC plus IB by IC. And here I can replace the IB by IC by beta. So so these two terms together will essentially give you IC times RC and IC times RC by beta, which means together they give you IC into RC plus RB by beta. And hence this equation simply gives you this particular value for IC. IC is VCC minus VBE divided by RC plus RB by beta. So now let us look at the beta dependence. Is IC independent of beta? Of course not. IC depends on beta through this term. But when will IC be largely independent of beta? When RC is much bigger than RD by beta. That's what you really want. But there is a problem with that. If RC is much bigger than RB by beta, then you will end up putting a huge voltage drop across RC, and because of that, if you look at the other biasing equation, which is the collector emitter voltage equation, you will get VCC minus the drop across RC will be VCE, and now VCE will turn out to be very small. Now why is that a problem? Because remember, VCE's bias value is what you have when there is no signal, but with the signal the VC value will start moving. Now if VC is already very close to 0, if you apply a signal and the voltage starts to fluctuate, you may very well go to negative values, which would mean the transistor will go into saturation or cutoff depending on which way you are. So what you are ending up with is a circuit for which you cannot really have a large output voltage, because the output voltage will actually become distorted. A circuit which behaves like this is really not what you want. So although this collector to base bias circuit is a good circuit as far as thermal stability is concerned, as well as beta independence is concerned, it becomes a sort of bad circuit if you think of its ultimate purpose, that of producing a large output signal. Now let us look at another attempt at improving the stability factor. Here we have RB and RC connected both to the collector bias battery VCC as in the fixed bias circuit, but what we have done is we have put in a RE resistance between the emitter and the ground. So strictly speaking, this is really not a common emitter circuit, because it's not the emitter which is common between the input and the output. What is connected to the input and the output both? Well, that may be a bit difficult to see here, because as I have explained, we are just looking at the bias here, so we don't have the input-output connected at this point. But you can imagine that the input will be connected between this point and the ground, and the output will be taken from the collector to the ground. So what is really connected to both the input and the output is the ground, which is this point, and the emitter is really not. So strictly speaking, this is really not the common emitter that we started with, but this is still called the common emitter circuit with an emitter bias resistance. Now this resistor added between the emitter and the ground also leads to bias stabilization, and let's see why. Well, if you just take a look at this loop, just to remind you, the straight line really is a loop. It's a loop which starts at the ground, goes to VCC, then comes down straight. You get VCC minus ICRC minus VCE minus IERE, or rather plus IERE, because by convention I is flowing in, is 0. And we want to write everything in terms of IC and IB. So what I will do is replace IE by minus IC minus IB, and that immediately gives rise to the bias equation. And this will give one equation. The other equation is what you get when you look at this loop. VCC minus IBRB minus VB minus plus IERE equals 0. So as I said, I will replace IE by minus IC plus IB. And if you do that, this is what this equation, the last equation, the base loop equation becomes this. VCC minus IBRB minus VB minus IB plus IC into RE. So you can easily calculate DIB DIC from here, which works out to be this, and this tells us what the stability factor is. The stability factor, just like in the collector to base bias, is an improved value over beta plus 1. It's a much smaller value than beta plus 1 because of this factor. Okay, what about beta dependence? Well, for that, we need to calculate IC from this formula, but that's also pretty easy. Just remember that you can ignore the IB here with respect to IC, or you don't have to. You just take IB, these two IBs together as RB plus RE, and just replace IB by beta by IB by IC by beta, and just rewrite the equation. You will get this. So the question now is, if I want S to be rather small and want IC to be significantly independent of beta, what is the basic condition? It turns out the basic condition in both cases is this, that RE by RB plus RE has to be reasonably large. Okay? Or beta times RE by RB plus RE has to be large. That's what you really want. And that really means this, beta has to be much bigger than 1 plus RB by RE. That will make this factor pretty close to, well, very big. That will also make this factor, RE plus RB by beta, pretty small. And of course, you can simply ignore 1 with respect to beta. Beta is pretty large anyway. So the condition really means beta times RE must be much bigger than RB for this to work. So for this circuit to be a good circuit, RB cannot be too big, because if RB is too big, then on the other hand, then this factor really ends up being rather small here. So the improvement on S is rather small. Also, if RB is very big, then this factor will not really be small compared to this beta independent factor, and so you'll have to take the beta dependence into account. So now let's worry about one more issue. What about saturation? Remember, the collector to base junction, base bias, ensured that the transistor would never go into saturation. But now you have to worry. Notice that both RB and RC are connected to the same VCC here, which means in order that the base go below the collector in voltage, the drop across RB has to be bigger than the drop across RC. So unless IB/RB is bigger than IC/RC, the transistor will go into saturation. But of course, since IC is beta times IB, this means RB has to be bigger than beta times RC. Now you begin to see a problem. If you want good stabilization, both good thermal stabilization and beta stabilization, beta RE, the quantity, must be much bigger than RB. On the other hand, if you don't want to go into saturation, RB must be much bigger than beta RC. You take both of these together, this actually tells you that the emitter resistance, the RE. Now the problem of having an RE much bigger than RC, which is what you need in order to ensure that you get improvement in stability and active mode operation. The trouble with this demand of RE being much bigger than RC is that if you look at this part, the equation that you will get by considering the loop which goes straight down here, the first equation I wrote down for the emitter feedback bias circuit, you will realize that this demand will really tell you that the voltage drop across RE must be much bigger in size than the voltage drop across RC. Remember, IE and IC are almost the same in size. So this resistance being much larger means a much bigger drop across this, and that will ensure that most of the voltage drop across CC or voltage of VCC is dropped across RE, and the voltage drop across RC is very small. Now that has two problems. If the voltage drop across RC is already too small, then if you apply a signal, which we haven't done yet, but we will, after all that's what this amplifier is for, what will happen is the current IC will go up and down, and if the voltage across RC is really rather small to begin with, fluctuating IC will drive that voltage down to zero. But that means that the voltage of the collector goes and hits the maximum possible value, which is the bias voltage. It will not go beyond that. So what will happen is your circuit will show significant distortion in the amplification of the input to the output, because the output will clip, because it will not be able to go beyond VCC. So that's one problem. The linear region of operation of this circuit is rather strongly limited. And as it will turn out, as we will see in a later video, the voltage gain of this circuit is sort of almost proportional to the voltage drop across RC. So if the voltage drop across RC is small, what will happen is the voltage gain of this circuit is very small. So this is a problem. A very small RC will reduce both the gain as well as the linear region. So despite improvement in the thermal stability, if you want this circuit to at all work as an amplifier, you want it to be in the active mode, and the two demands together conspire to give you a rather bad amplifier. So that is a big problem. However, let me point out that the real issue here was I needed base to be below collector. Why did I demand that the drop across RB be more than the drop across RC? That's simply because at their other ends, both the resistors have the voltage of VCC. So it's actually very easy to have the best of both worlds, which is I can have improved stability and ensured active mode operation. All I really need to do is, instead of starting this end at VCC, I start this end at a much smaller value. So all you need to do is use a smaller, separate base bias battery. That will ensure that this end is already lower than VCC to begin with. So coupled with the drop across RB, that will ensure that this base is much lower than the collector to begin with. So no worries about saturation. But just remember, using a separate base bias battery, what does it mean? It means that in addition to this transistor, 3 resistors and a single battery, you have to use one more battery. As I have said, the battery is the single most expensive part of the circuit. Using 2 batteries will effectively double the price of the circuit. Not a great option. But there is one thing which allows us to actually trick the circuit into believing that there are 2 batteries when there is only one, which is this. You simply use a potential divider between VCC and the ground here, made out of the resistances R1 and R2. And if you do that, then what will happen is pretty easy to understand. If, let's say we put this whole thing in a black box and then try to just use Thevenin's theorem, I will get a Thevenin voltage, which I have written down as VBB here because that's what it will do. It will bias the base of R2 divided by R1 plus R2 into VCC, and a Thevenin resistance, which will essentially be the resistance RB of R1 R2 by R1 plus R2. What have we achieved? We have achieved the situation that VBB is a much smaller value than VCC. I can of course choose how much smaller by choosing R2 and R1 judiciously. These are all parts of designing your circuit. But now you have a situation where you can use a smaller battery without incurring the extra expense. And that is why this happens to be one of the most popular simple transistor amplifier circuits as far as DC bias is concerned. Of course, we still have to connect the signal and take the output to make this a proper amplifier. But this circuit is really one of the crowd favorites because this has simple operation, simple design, improved bias stability, improved beta independence, as well as a low expense because you're not using two batteries, you're just using one. So in the next lecture, what we are going to do is take a look at what happens when we take an amplifier circuit like this and actually connect the input signal. So we will be discussing the proper amplifier action of a transistor circuit starting from the next lecture. Until then, goodbye.